how to configure an underlay network. Welcome to the Underlay Network module. By the end of this module, you should be able to explain how to configure an underlay network. Underlay network of a collapsed spine fabric provides Layer 2 and Layer 3 communications between the fabric devices using Ethernet interfaces. The underlay also exposes the loopback interface address to the other spines, which is required for the overlay network to be established. Link aggregation group interfaces on the access switches combined with Ethernet segment identifier link aggregation groups, or ESI-lags on the spines, provide redundant load sharing. Here you can see the first configuration step toward establishing an Ethernet VPN Virtual Extensible LAN, or EVPN-VXLAN network. We assume that there is Layer 3 connectivity and reachability between the spine nodes, and the loopback interfaces are configured. In this example, external BGP or eBGP is used as the underlay routing protocol. Before configuring eBGP, an export policy is needed to identify the loopback address. Here you can see one example of this policy. This policy is then applied to the eBGP group. The loopback interfaces are used by the internal BGP or IBGP overlay to establish the EVPN session. The BGP configurations for both Spine 1 and Spine 2 are shown here. Private Autonomous System or AS numbers 65101 and 65102 are used in this example, and the connected interfaces use addresses in the 172.16.1.0/31 address space. We have also set the underlay for IPv4 advertisements only. If you require IPv6 peering, you could either add the family iNet6 or not limit the advertisements. When we configure the overlay, we will limit the overlay advertisements to EVPN signaling. Once the eBGP peering is configured, verify that the peering session is established. Using the show BGP summary command, ensure that the state is established and that the inet.0 table is receiving routes. The loopbacks should be visible in the inet.0 routing table, also known as Routing Information Base or RIB, and can be viewed using the show route command. Here, everything looks good. You are still working at the physical layer. The access node interfaces connected to the spine must be configured as lags. This will be covered next. When configuring access switch interfaces, there are two types of port configurations that must be considered. There are access ports and trunk ports. Access ports face end systems that connect into the network at the edge. While there are additional security concerns that should be taken into account when configuring these ports, this course does not cover those concerns. Refer to the Junos Enterprise Switching and Advanced Junos Enterprise Switching courses for those details. Trunk ports can carry traffic from multiple VLANs and are commonly used for uplinks to the core and distribution tier. In a spine-only architecture, the ports that face the spine tier are configured as trunk ports and are established as lags with one or more links connecting to each spine node. This example shows the configuration of the Access 1 node. While there is only one VLAN configured in this example, multiple or different VLANs may be needed, depending on the devices connected to the node. Access nodes will have many end systems connected to their interfaces, and in an existing network, these interfaces should already be configured. During a transition, any changes will probably be to the uplink ports. Spanning tree may be configured on these ports and will not be needed in this new design. These ports will be configured as trunk ports and will be made a part of a lag. The link aggregation feature enables you to aggregate one or more Ethernet interfaces to form a logical point-to-point link known as a lag, virtual link, or bundle. The Mac client can treat this virtual link like a single link. Junos, by default, does not have lag interfaces defined. Once created, these Ethernet lag interfaces are referred to as AE interfaces, where X is the interface number. These interfaces are created by configuring Junos under the chassis hierarchy and specifying how many AE interfaces will be required. The first aggregate interface is named AE0, and if more than one interface is allocated, then the subsequent interfaces will be named AE1, AE2, and so on. Once the lag interface is defined, physical interfaces must be associated with the aggregated interface. The Link Aggregation Control Protocol, or LACP, works with lags as a signaling protocol. When LACP is not enabled, a local lag might attempt to transmit packets to a remote single interface, which causes the communication to fail. When LACP is enabled, a local lag cannot transmit packets unless a lag with LACP is also configured on the remote end of the link. The lag interface should be configured to support LACP and start communications to the other side using the active option. In addition, the port should be configured as a trunk port that enables the specific VLANs used by the access ports to be forwarded across the link. The configuration shortcut keyword of all can enable any VLAN to traverse this link. In this example, Access 1 and Access 2 support a single VLAN for the connected users, and the lags facing the spine nodes are configured to accept all VLANs.